in the sense that this is more like a hype you up style course. And like I said, I'm kind of trying to review the course and seeing what my speed is nowadays and how fast I can talk and so on, right? But the first week is always like, okay, what do we try to aim to do in this course? So introduction, mainly set the scene, get you hyped up, right? So setting the scene, what are the components of data science? What is this actually about nowadays, right? And again, I'm still trying to choose this name data science, even although it's a little bit outdated, right? But what else would we call ourselves, right? If you are interested in this, prompt engineer, right? Vibe coder, that's, yeah, sure, maybe the components of vibe coding, you can do that, but it doesn't sound so scientific. So still, data science sounds a little bit more scientific, right? So that's what we try to do today. I've been trying to make history slides, and I'm also trying to summarize them in some sense, because if you look at it and you look backwards, we have come a long way. And I think maybe for you guys, if I would ask you, okay, maybe even without showing that slide, so that you're not biased, right, which is always a danger when you work with data. If you think about data, AI, machine learning, predictive modeling, statisticians in the room, what got you interested? I'm actually kind of curious. You're young, I'm much older. What do you remember that was your first moment in the sense of, wow, computers can do that? Or wow, statistics can do this? Yes?
Asymmetric control for program evaluation.
Good answer. Nice. Anyone else? Why you're here? Well, don't look away. You're here to study, I know, because you have to. It can be crazy, right? You can say, I saw a Redstone video when I was 12. Huh? Or I saw a Veritasium video about a Turing machine made of water. Or I saw the match between Lee Sedol and AlphaGo. Anyone? Or I remember when the first ChatGPT version came out. That's not that long ago, right? It's not that long ago. I remember IBM Watson playing in Jeopardy. So why you're here? Yeah?
I remember with a simple linear regression, in 30 seconds, I had an answer. I could have worked a month on it.
Perfect. What was the software that you used?
R.
Good. Anyone else? I trained a neural network on black and white images on an old computer. You want to say something? That is pretty cool. Yeah, good poker players, right? Yeah, yeah. Well, I think today we call that the cryptocurrency market. Yeah. So you should be here for something, right? I mean, it's going very rapidly. Again, this is a short history. I mentioned a couple of things. 2011 is IBM Watson playing Jeopardy. A horrible decision-based system, no deep learning yet, right? Funnily enough, I could have put self-driving cars on the same year, because already since 2011, people have been trying to do that up until today. It's coming, sure, even although Elon Musk is not that interested in cars anymore, but it will come. Cars are harder than you might think. 2012, AlexNet. right? The first convolutional neural network reinvented after it was been invented before, but GPUs and more data and a huge breakthrough. And then the Go match, like I said, against Lee Sedol. That was deep learning inspired. So this is a bit of the DeepMind overview, right? Because they're not doing that bad. They went further and further. And today, they're inventing new materials with the same technology. They're inventing or they're solving mathematics questions, Erdos problems with agentic AI. Not out of the box. You can't just prompt ChatGPT and ask it, please solve this problem. You need to use a specific programming language for that called Lean, which they use to solve mathematical problems. But they're doing this. And is it AGI? Right? Probably not. Probably not, but it's pretty nice, right? So DeepMind and Google, better weather models also. And of course, fun stuff like Nano Banana Pro, right? And Gemini and Gemma. By the way, anybody knows what is the difference between Gemini and Gemma? Yeah, you? No, not really. Gemini and Gemma. Yeah? Yeah? Some of them are. And Gemma? Yeah. Yeah. And the key thing is that Gemma is smaller. Yeah. Yeah. So, not to be mistaken, there is a big push against or towards larger and larger models, but also smaller models. Models that all of you can run, and hence also at Simon Tree, it's time, I think, and I know I will get complaints, but models that you will be able to run on your own machines. Microsoft has released BitNet already a couple of years ago. 1.5, which theoretically doesn't exist, but 1.5 bit models basically means you have 3 weights in your model, either minus 0.5, plus 0.5, or 0, and with that you can do everything, right? But there are also things such as Air LLM, which dynamically load in and load out layers on your SSD. It will take a while, sure, but you can use them. So what a world. Meanwhile, Anthropic is also keeping busy, and OpenAI, apart from DeepMind, I respect DeepMind because I think out of all the AI companies, if you look at it backwards, we chat a lot at 3 a.m. with ChatGPT about our personal problems, but I'm not sure if it's helping a lot to humanity. So DeepMind does better there. Yeah, these guys, they're trying, right? Multi-agent, imagery, generation. Anthropic is thinking about changing their name to be Misanthropic, right? But cool stuff comes out of there. And then there is the danger from China, right? DeepSeek, Kimi, what is it? Kimi 2.5 or something like that, right? Yeah. So stolen weights or not, I don't know, I don't care, but they work, right? And good on them. So they also release a lot of models that are being open sourced, well, open weighted and usable for all of us, right? So we live in a bit of a crazy world right now. And we live in such a crazy world that you might think, well, I cannot catch up with them. And so do I, to be honest. You try to import a Hugging Face library and you do something on your own machine, and meanwhile that old, boring tabular learning, who cares, right? Or old, boring statistics. I'm happy that you gave the answer of a linear regression, to be honest. That's still the magic in there. So is there still room for this boring tabular data? And at least for the first weeks, I will be here to tell you that yes, there is. because I'm old and stubborn, I refuse to give up on it, but also because there have been some new, well, newish algorithms that came out that you can utilize. Things actually have become quite simpler on the algorithmic part. And it's sometimes, to be honest, a mistake that we as university lecturers make. Who had a course on support vector machines? 1, 2, 3. Okay, that's good news. That's less than before. Naive Bayes. Also a couple. Decision trees. Good. LightGBM. TAP PFN. XGBoost. Better. So, in the first part of this course, we will go over very quickly the very basics of supervised learning, but just to get it out of the way, and then LightGBM, CatBoost, XGBoost, TAP PFN, right? If you work ever again on a tabular data set, those are the techniques that you should use. And the rest, to be honest, if you work for a consultancy company or a startup here in Leuven or in Ghent or in Brussels, even if you do something more specific like recommender systems or time series analysis, that's what they will all use, right? Like I said, it's a bit boring, but it's still the majority of use cases today. Because there are still a lot of use cases being explored. And you can see them listed here. Whatever field that you work in, marketing, fraud analysis, which is something that I did a lot of research in, but also web analytics, logistics, and so on. So always that easy, and that's actually also a claim that we will make later on, to gather the data, prepare the data. That's 80% of the work. But once you have done that 80% of the work and you have your data ready to be analyzed, the algorithmic part, you should know how it works, but at least we're not anymore in the area of I should try with RapidMiner or AutoML 30 different algorithms and then hope for the best. No, we have proven techniques there, right? So again, that's good news, right? So which techniques to apply? There are only few left for this type of data. Is AI eating the data scientist's lunch? In a way, right? I will be honest, if I also teach not just to master students like you, but I also teach to first-year bachelor students. Remember when you were very young, right? And much more, 650 students in a room. They have grown up with AI, right? And sometimes even for tasks like you need to analyze something or you need to do something, the suggestions are not all that bad. So another key point that I hope that we will go through is be critical and dare to ask, like, is this right? Is this wrong? What are the benefits of using this versus what are the disadvantages of using this, right? Then big data, still relevant. It's a little bit solved. It used to be a hot topic, big data. Nowadays, you don't hear a lot about it anymore. Big in the 4 or 5 or 6 or 7 V's of big data: volume, veracity, variety, velocity, and so on. Value is then the 5th one. It's a bit soft, we should admit, right? We have cloud databases, we have Snowflake, and so on. We have ClickHouse, we have Supabase, right? We have Firebase. So that is a little bit soft, true. But learning about the underlying technologies is still something, or at least the tidbits of that, like how do you set up a database in a distributed fashion, is still something that we'll also discuss, right? In terms of components, that was a question that was asked. Difference between text mining, text analysis. That's a slide for that, right? So data science, I still like that term. Otherwise, data mining, big data, data analytics, knowledge discovery, AI, ML, decision science, machine intelligence, deep learning, no one knows, right? It's all kind of the same, right? I don't want you to remember any definitions about this, right? That will not be a question, I promise you, that you will ever get from me. Like, give me the definition for data science. Except maybe like, we all know what it's kind of about, right? We all know that data, the fuel that we use, right, or we plan to use, contains value and knowledge, right? Also, there is a bit of an interesting story because I'm involved with a new organization coming from the Belgian government called Flanders Make, and they try to align research that people like me do with industry, bring us together, right? What you hear is that a lot of industry in Flanders is very customized, right? It's small scale, it's little volumes, and it's à la tête du client, meaning depending on the phase of the client, right? So every client comes with their own requirements, and that's what we're very good in. It's a bit sad, but because what I will always say in those kind of meetings is we want to predict if this kind of run that we do on our machines, will it fail or will it work, or how do we adjust these knobs that we have? Give me examples. Do you have historical examples? Well, yeah, we have about 20, 30 per year. And everything is different. Sorry, but that is not something that you can learn from. So in terms of volumes that we speak of and things that we can do, data that we have, right? We're here for the data. If there is no data, if we don't have the volume to learn from, you can do risk analysis, you can do like extreme event analysis in statistics. Perfect. In economics, they do need a lot of people like that, especially nowadays. But for us, we're kind of stuck then, right? So we are here starting always from data. And we admit that it contains value and knowledge. But we also know we have some problems with that. Data in itself, it's not oil, right? It's not gold, right? There used to be slideshows and marketeer talks telling you that oh, data is a new oil and it's a new gold. Bullshit, right? Even gold, yeah, you get it out of the ground and it's immediately valuable. You can make jewelry out of it or something, it becomes more valuable. Oil, you can get it out, you put it in a barrel, you need to refine it. That's maybe a little bit closer because data, a lot of companies are sitting on data, right? And it's not immediately valuable. You need to work for it, right? And more than just refining it and putting it in a barrel, right? And that's the biggest lesson. Data in itself is a liability. It's not an asset. It's a liability, right? And it takes culture, effort, management, leadership to do something with it. So what do you do with your data? Well, store it. That today, it used to be different, but that today is the easiest challenge, right? Storing it, well, maybe not. In a couple of months, RAM prices are going up. Maybe the rest will follow. Things change, right? But storing today, yeah, it's somewhere in our data lake. No one ever looks at it. So it's there. We don't know what to do with it. Used to be different. Like I said, in the 80s, 90s, storing was the biggest cost. That has changed. Okay, so we have it. We need to manage it. Ah, that's already a way bigger question. What do you mean we need to manage our data? Well, it can be as simple as asking the question of discoverability of your data. In every company that you will go work for, or do your thesis with, or talk to people, that will be a huge issue. Discoverability of your data, once you reach a certain scale, that's going to be a challenge. And then, what we are most interested in, analyze it. And that can start relatively simple. Business intelligence, right? We have Power BI installed, we have ClickView installed, right? And we make some dashboards and we make them real time and they like it. In every company, still today, and it's a bit sad that I have to tell this, in the age of AI, where on the one hand you have managers saying we need to build some RAG system with knowledge discovery for a chatbot, there is another department which is still getting started with making a dashboard, right? For what? Discoverability of their data. This we will move past. Not too much in this course. What we want to do when I say analyze is we want to do predictive modeling. That's a key thing. We want to use our data to ask meaningful questions, the right questions. Some questions will be wrong or stupid or not necessary, right, to predict something. Preferably in the future, because predicting something that has already happened is, well, easy. So these terms, they're used in between, interchangeably. Don't worry too much about them. Just to prove the point, here are some pictures. I don't want to blame the specific person that put this online, but I mean, the overlap between data, features, and algorithms is machine learning. It's crap. I mean, no one gets anyone. And what? Features and algorithms is classical programming? Doesn't matter. It doesn't matter, right? And you will laugh, and if you ask ChatGPT, will also come up with a bullet list like this, and it is not this, it is that, right? But no one cares. What people care about is this, right? Value, knowledge, do something. This is an older one. When I was making these slides, I tried to find a more up-to-date one, just to see if my jokes still work in 2026. So this is the newest one, up-to-date, with even ChatGPT has a little bubble there. I don't know, right? It's kind of right in a sense that, yeah, unsupervised learning indeed has variational autoencoders and GANs, but not fully, and then this is generative AI. How pity about the symbolic AI people though, right? They're all alone by themselves. I was going to put Jan LeCun in there, but he's not even in there. He's more working on his world model. So there are still some symbolic AI people that even in this diagram, they're like separated out. Maybe they'll have a comeback. Let's hope so. So don't get too much swayed away by that. So what are components, right? Speeding up a bit. We have lots of data, or a little bit of data can be enough, sufficient, right? Not 20 examples, story, statistics people, but we have sufficient data. And we want to either discover patterns or models from data. And that's already a bit of a separation. Patterns is typically linked to the unsupervised style of modeling, right? Where you cluster things or you find rules. Models is a bit more upfront. You have an input and you want to predict some output. The key items being, we will not sit together in a meeting room and from our gut feeling or belly say, well, today we should target this kind of customer group or tomorrow we should come up with this kind of promotion. We will let the data speak, right? So that's what we use those algorithms for. We have historical data, and again, you do need to have that. If you don't have that, then sorry, right? And you will all go like, yeah, for sure. Sure, that makes sense, right? Otherwise, why would you do this? You would be surprised in how many cases you need historical data. That's a bit weird, right? To predict something. Or, as a first step, maybe explain something and hopefully maybe even decide something. We use data. Those are 3 ingredients, right? If you cook a recipe, 3 ingredients is data, algorithm, purpose. And at the end of the day, if you have cooked something, you want it to taste nice, right? So how do we know that it tastes nice? It needs to be valid, useful, unexpected to some degree, and understandable. What does that mean? Using data, that's how we will kind of guide our course. That's our first ingredient. Data, tabular data. That's what we will get started with. Structured, as we will also call it. I don't like the term unstructured versus structured, but okay, if you say structured tabular data, instances, your rows, your examples, your observations, and attributes, items, features describing your observations. Easiest thing to get started with, but also later on, images, text, audio, graphs, video, right? If you want to build a world model, if you want to build Genie, a DeepMind, you take in the whole lot of YouTube and you build a world model. Just pump it in as raw features, as raw as can be in that sense. So that's our first ingredient. And that's what we'll use mainly to structure the next weeks, right? So data, one ingredient. Second ingredient, well, data, like I said, structured, unstructured, I don't like those terms. I just like to call the data what it is, right? So you have tabular data, that's what we all know, or you have imagery, you have video, you have audio. Don't say structured, unstructured, it doesn't matter anymore, right? Just name it as it is. Now, that being said, if you have non-tabular data, what we will see is two ways of handling that, of tackling that. One way, which is the more traditional way, is, well, we have unstructured or non-tabular data, like we have audio files or images, let's make it tabular. Let's do some feature engineering. Let's do featureization, right? Can still help a lot, right? If you do a lot of work, or if you put a lot of work into feature engineering, right? Once you have those features, once you have those attributes, and then you take one of those models that I just mentioned, like XGBoost, you can do a lot, right? So not to be forgotten. The other style is, well, we just dump it in raw as is, right? And even then, some structure will be there, but that's what deep learning then came from, because the whole promise of deep learning was mainly like, you can just take your data and dump it in end to end, and it will learn, it will do the feature engineering automatically, right? So, in terms of things to remember for today, this is for the next week or two what we will work with, a tabular data set. So, structured, if you want, data looks like this. You open it up in Excel, right? So, the rows, everyone in machine learning will call these instances. I know in statistics you call them examples or observations. I don't know why, machine learners like to call these instances, right? The instances that we learn from. The columns or attributes, fields, variables, predictors, whatever, in machine learning, we like to call these features. Instances and features. The first column you see here is unnecessary in the sense that we don't use this for learning, right? Because the model that we would fit would overfit on this. That's just for us that we can retrieve, or we can give every row a unique name, basically, right? That's the index in your pandas data frame. Pandas, Python, who has worked with this? Good, you will need that. Then there is also a target that you will need to predict, right? In the case of supervised learning, play golf, yes or no. And in terms of our features, we can split them up further. We can say, well, some of these features are numerical or continuous numbers, and some of them are categories: categorical, discrete, nominal, ordinal, factor, or factor, ordinal, or binary. Yes, no, plus, minus style of features, right? Weirdly enough, there is no specific category for integers, right? Which is a weird mix between the continuous and the categorical, right? No software does that. So we just also treat it as a number, I guess, continuous. Target can also differ. Here it's a yes, no. So it's a binary target. The majority of tabular supervised predictive modeling cases are still binary supervised learning, but can also be different, right? What if you have more than a yes or no, right? Then you have multi-class. What if it can be multiple answers at the same time? Like instead of giving you a row, I give you pixels of a picture. Please predict me whether there is a dog, cat, or horse in the picture. But more than one can be present at the same time. Then it's multi-label rather than multi-class. Multi-class is one out of these three. Multi-label is any out of these three, including none. Right? Or you try to do a regression style analysis, then your target is numerical, continuous. Right? So given inputs, you try to predict something. That's what our data set looks like. So we have a tabular data set with instances, features. The features can be numerical, continuous, or categorical, discrete, factorial, and so on. And then we have our target, or dependent variable, if you will, or response variable, if you will, right? Also of different forms. In some cases, you can have even rarely seen in traditional machine learning because the algorithms are not suited for that, although there are ways to set it up, but you can have more than one target as well, right? If you want to predict bounding boxes of an image, you predict the upper leftmost coordinate and the top right, or bottom right coordinate. Yeah, you have two outputs. Also easy to set up with neural networks, a bit harder to do with traditional models, right? So there's not always just one target. You might have a multi-target thing going on. And then we use algorithms. That's our second piece of ingredients. So we have the data first, tabular, bit simple. Our second piece is algorithms, right? Again, bad slides here. MathWorks, which is not that bad, but they had a quiz at some point. What type of machine learning algorithm makes predictions when you have a set of input data and you know the possible response? I don't know. I think both deep learning and supervised learning can apply there because deep learning is or can be used as a supervised learning technique. So again, don't get too swayed. How will we categorize algorithms? Two main pieces or categories that we'll go through. When we talk about generative AI, we'll kind of be in the middle a little bit, but typically people like to divide learning algorithms in two categories, one being unsupervised and the other one being supervised. Biggest difference, unsupervised means this target column that we saw before, not necessary. We don't have that. Unsupervised just means, well, we have data and we try to find structure in that data, or we try to find patterns in that data. And the nice thing is that here in terms of algorithms, you have a lot of variety because then the question is, what does structure or patterns mean for you? Does it mean that you want to find a grouping? Now you're talking about clustering, for instance, or does it mean that you want to do some sort of dimensionality reduction? You have data with 200 columns and you want to reduce them down to 2, right? And use PCA, right? Or UMAP or t-SNE, right? Or you want to have purchases from some basket analysis that you're doing and you want to do some sort of association rule mining, right? So here you have data and you want to organize it in some way. You want to summarize it in some way. You want to get some insights out of them. The other one is actually simpler. When you talk about supervised machine learning, there you have way more algorithms available to you, especially in the tabular field, right? If you open up scikit-learn in Python, they have lots of algorithms for that. I will tell you later that only a few of them really matter. But there is, okay, we have our instances with those features, those columns, right? And we want to predict a target. And you have different algorithms from SVMs to decision trees to XGBoost to LightGBM to a neural network to whatever. But the goal is the same. Given inputs, predict me the outcome. That's supervised learning. And again, meaning that you do need to have some historical examples available, right? And it's a bit weird. I will say a bit more about it in a second, but you do need to have that to train your model on. Use cases, churn prediction. Predict me which, given that I take a snapshot of you today, I have a noodle shop, right? And you come every week and I take some attributes of you. What do you normally buy? How often do you come? What do you spend, right? Maybe how old you are, you have a customer card, whatever. And then I keep track, and I see that some of you do not return back to my shop. And I think, well, weird, what happened to them? Maybe I can use this historical information that I have to predict now, based on the snapshots of the customers that I have now, who will also leave me 1 month from now, right? That's supervised machine learning. And I said before, typically we try to predict something that will happen in the future. Why? Because obviously those are the interesting use cases. And a lot of tutorials and textbooks make mistakes on that, like even the stupid play golf example that I gave you before, right? If you saw it in the tabular example, is the temperature nice? Is it windy, right? Is it cloudy or not? You don't need a model for that. You can literally just look outside and you know, right? No one will use that model. So typically, and that's a bit of the hidden angle there, the most interesting models are the ones that are capable to make a prediction a little bit forward, right? Based on a snapshot of a customer that you have today, only today, what will happen in the next few days or in the next few months. Of course, the accuracy will not be that great, right? But it will be more useful to you. Now, these are the two categories. There is also, semi-supervised reinforcement learning. Recommendation systems is maybe supervised. Well, yeah, I guess it is. There is also self-supervised, right? If you think about the whole generative AI hype, that's all self-supervised. We don't have a target, so it's unsupervised, but maybe we can come up with a target. I have the whole Wikipedia downloaded. There's no target there, it's just a data set. How can I pretend that I have a target? Well, I give it the first 4 words of a sentence. Please predict me word number 5. You have a target. You have a whole bunch of images. What happens if I randomly blank out a piece of this image and I train a model to fill it back in? Right? That's self-supervised. It means you start with a whole bunch of data and you create some sort of intrinsic target from that. And that's the whole drive between or behind the foundational models that we have today. It's exactly those kind of things. ChatGPT started as, well, can we train a model that predicts the remainder of a sentence? Right? You do need a lot of data to make that work again. So with supervised learning, going back, well, again, if we look at the target, again, splitting it up further, 2 styles, classification or regression. It's pretty easy. Regression is a continuous label, right? Linear regression and other types of regression. Classification is you have a categorical label. Binary classification, which is what the most tabular learning techniques are built for and the most evaluation metrics have been built for, is what we have available. And typically what machine learners try to set up every use case with, right, because of those reasons. So it's a yes or no outcome, a positive or a negative outcome. This person will, or customer will churn yes or no. This claim in my insurance company is fraudulent, yes or no. Typically with a probability attached to that, right? It's 90% positive, it's 70% positive, right? Majority of use cases. But you can go further. Like I said, you have multi-class, couple of different outcomes, and you pick one out of the outcomes. Ordinal classification, when your target is ordinal. Example, credit ratings. Will this country, Belgium is currently, what is it, AA? Let's hope, right? Where will it go towards the future? A or AAA? That's an ordinal target. There is an ordering in the categories that we have. Or multi-label. Multiple outcomes are possible. Remember the picture, cat, dog, horse? Well, there is both a cat and a horse in this picture, right? And multi-output as well, except not often seen in traditional models. That's one way to split up the categories that we have. There are other ways as well. Another way that people will sometimes discuss is, well, you have discriminative models versus generative models. when people say discriminative, they say, well, they directly model the relationship between the input and the label as a function, as we just saw. Right? Given the inputs that we have, all those features describing my customer base, I try to predict something. I try to find a good decision boundary, splitting the no's from the yeses. You could also say, well, I have more of a, and there is that name, generative model. What if I just mix everything together, both those features and those targets, and I model a joint probability density? And later when we look at autoencoders and variational autoencoders, that's exactly what these things will do, right? And then why not mix those targets that we have in between to model it as a joint system? There are other ways as well. Parametric versus non-parametric. Well, parametric, to be honest, I don't really know. Parametric, you specify the parameters beforehand. And if you talk about linear regression, ordinary least squares, for instance, everybody will tell you that's a parametric model because you estimate the parameters, right? You estimate the weights. How about the deep learning model with 8 billion weights? That's also a parametric model because you also estimate the weights using some optimization procedure, namely stochastic gradient descent. So this, it's a bit weird nowadays, right? Parametric, I think most of the time people, when they say parametric, means understandable. You can inspect the parameters, right? You can plot out or print out a coefficient chart or something like that. But most models come with weights. Even, you can even model decision trees as a parametric model if you want to, right? So everything is parametric. You have the parameters and you have the hyperparameters. That's it. So supervised learning, we will use the data and then a model comes out. And here we have the decision tree, which most of you know, right? If you don't, we'll go through that pretty quickly later on. So historical examples, we let the data speak and a model comes out, preferably understandable, like here, something that we can follow top to bottom, not always. Unsupervised learning, we extract patterns from the data as is. Examples, clustering, association, I already mentioned. Dimensionality reduction is something important that we'll go through because that will easily link us into generative AI, weirdly enough. But also anomaly detection. Isolation forests and things like that. Very often, or there are some cool techniques that we will discuss where you also do not have a target and you have a use case at hand where you want to find anomalies in your data set, but not in a univariate sense, right? Because that's boring, that's your standard z-score or box plot. Typically, data is a little bit more complex than that. What can we use for that, right? And even if we do have a target, like fraud, where this shows up often, right? If you think about insurance fraud again, for instance, can we give some anomaly score or can we calculate some anomaly score that will help us as an extra feature, right? Now, what you do see in unsupervised learning is that a lot of these are based on frequency counts or based on distance metrics. That's the nature of how this works or similarity, and that will come back again and again. Even if we look at dimensionality reduction techniques such as t-SNE later on, it will basically also be a similarity measure that's at the ground level there. Okay, last ingredient, purpose. Data, an algorithm, and a purpose. And that's, of course, the most important one. Because you can say, or this is how it's often discussed, okay, unsupervised learning, that's for descriptive analytics. And supervised learning is for predictive analytics. Well, no, not really, right? It's not the same. The question to ask is, given that you would already have a model, it works perfectly. Given that you reach your end result of this tool, technique, algorithm, data, whatever that you plan to use, how would it look like in a finished, concrete end product? That's your purpose, right? Think backwards from the end instead of, and that's still also a mistake that you see many organizations making. because they have seen some flowchart somewhere, and they start with the data, and we need to go hunt for data, and then they go with their project manager and their architect on a pathway for a year. What do you plan to use it for? What's the purpose? Right? And what is this thing in the end? And there are a couple of answers to this. Exploratory, descriptive, explanatory, predictive, and prescriptive, right? And if you would try to draw the lines between these items and unsupervised versus supervised, you can mix and match in a lot of cases. Example, maybe a bit over your head, but we'll see. Explanatory, well, typically you would use a white box model for that. It's, in that case, perfectly fine that you take your historical data set, you don't even split into a train and a test set, because you're never planning to use this model in a predictive environment, right? You just train a decision tree on the data that you have, a couple of levels down, to help you explain something, to get an insight in your data. The big barrier that you step through is from the moment that you will decide, or that you think, or that you hope, or that you wish, this is not just a model that I train one time to help me explain something, or help me do some exploratory analysis, or describe something, but something that has to be repeated or used going forward in the future. That's when models become predictive. That's when they need to be utilized in inference. No matter what's in your pipeline, even you utilize an unsupervised technique like clustering to generate some features because they work well, from the moment that's a model that you want to have run every week, it's part of your pipeline. It's part of a predictive model then. Right? So it's not between unsupervised, between supervised. It's about, is this something that we will have to keep running going forward and using, or just a one-off analysis because I want to get some insight in my data? Right? Prescriptive, yeah, that's the hardest one, the bottom one here. What should I do? To be honest, there is a whole field about prescriptive analytics, but it's kind of well, a downer, to be honest. Up until today, I think there are two answers. Either you take a good look at your features and you see what are the ones that I can manipulate as a process owner, as a business owner. There are some things that you cannot manipulate, right? Like the age of your customer, you will not be able to change that, but maybe some promotions that you're giving and so on. Also depends on the features that you put into the model to begin with, and then you do some kind of what-if analysis. Some simulations like, okay, I have this customer, they're not happy with me, they want to leave, or a whole bunch of customers that my model predicts that they want to leave. But what if I give those guys a promotion? What would my model say then? Right? And based on those analyses, you try to see what are the best courses of action. Right? That's one style of prescriptive advice that nowadays people try to get from models, but it depends heavily on the features that you had to begin with. The other style is to go for, well, heavy foundational models, large language models, and ask them, but to which extent is it hallucination versus really being prescriptive? I'm not sure. Right? People are doing experiments with using LLMs to do stock trading and so on. If you only do that for 4 weeks, I don't know, right? Typically, there is also, or what you also have is good old operations research, which is heavily invested in those kind of optimization questions. So also not to be forgotten. And there is still a room for merging machine learning with operations research, still today. That is an aside. So to hammer the point, the question should be, don't worry so much about your data, your algorithm, your pipeline. Pretend for a little bit that you have your model. Whatever question that you ask. If you sit in a meeting, we need machine learning, we need AI for this. Okay, tomorrow it's done. We have a trained, validated model, and it works. How will it be used? Where exactly in your existing process will you put that model in? That's the purpose. And if for that you do not get an answer, you should not start training. If you do get an answer, then you can ask questions such as, okay, so you do want this model to be continuously used. What's the retraining look like? What's the maintenance look like, right? So don't be surprised. A lot of people just start from data, and that's a big mistake to make, right? Oh, we have so much data. Yeah, everybody has a lot of data. What's your goal? Why or where do you want to plug this model into, right? So the purpose is key. Also, you will notice if you work in business that a lot of questions that you will get when people tell you we want to use AI or machine learning, that they're not so much talking about the intelligence of the model itself or the predictive capabilities or the accuracy. In the most cases, these questions stem from a need of automation, which is fine to work on, but then maybe also not something where you need to utilize a reg and a chatbot and and Moldbook and what else do I know, right, on that. Organizations are willing to automate, and the ML component is typically a small piece in that whole process that they're discussing, right? So that's critical to try to dare to ask, what are you planning to use this for? And then you will figure out that very often it's just about automizing or automating some part, okay? I'm not the first one. This is, by now, these are older quotes, 2019 and so on, but also from Google. Google at one point had a rules of machine learning guidebook. And their number one rule, do not be afraid to launch a product without machine learning. Probably today, if you will ask them, they would tell you something different, or at Amazon or Facebook, everything needs to have AI, right? And that's maybe the AI bubble that we live in. But not everything is about this, right? People want convenience, companies want efficiency, right? And typically your ML part that you're doing, and those are typically also the best use cases that you can work on, when they're a small part of being a cog in a machine and oiling the whole thing, right? Other quote, increasing the performance of a model does not necessarily translate into gain in business value. There will be a point when you are focusing on optimizing accuracy or your area under the curve score, when your business users, your stakeholders, have long left, right? Because first of all, they don't understand what AUC means. Second of all, they have their own estimates and their own ways of working and their own Excel sheets and high sky expectations, right? You go ask them, well, what do you expect that the model does? Oh, we only make a mistake 1 out of 100 cases. Yeah, why is that? Because you filtered your list already so much that you only have 20 people left every month to contact. Of course, you only make 1 mistake out of 100, but you're only zoomed in into a little bit of your customer base. So expectations management and getting the questions right. So those are our 3 ingredients: data, algorithm, and mainly purpose. Then the dish is done. We need to taste it. Or key criteria. But first, 15-minute break. Learning from statistics, the models that we built need to be generalizable, right? Tomorrow there is unseen data. There are new instances that we want to apply our model on to predict us, give us some sort of output, a probability or whatever. And they need to retain some sort of their predictive power. That will not be forever. Main thing is over time. won't be forever. At some point, we do need to retrain our models or maintain them in some way. Every predictive model that we have loses power over time, right? Even if you think of something like, well, the line has become a little bit blurred, but let's say something like ChatGPT. If you take GPT-2 and you ask it about COVID-19, it won't know what that is, right? Because nothing happened yet. It's not in its weight. It can hallucinate something, right, and make it seem reasonable, but it doesn't know. Why I say the line has become a little bit blurred is because these things can do web searches now and incorporate live feedback. So maybe that's blurring a bit. Nevertheless, every parameter of models that we train stays fixed in the time it was trained. No matter if it's a linear regression model with only 6 parameters, 6 weights that we train, up until an LLM with 8 billion weights, right? Those weights are fixed, right? It's not self-learning. It's not continuously learning. That's all marketing speak. Once the training is done, models stay in their kind of training regime, their training environments. They don't continue to learn forward. They don't adjust themselves, or they can pretend to be because they take something in their memory, things that you have talked about them before, but the memory then being just put in the context and feed it back in again. The weights stay the same. Nevertheless, we do hope that models that, obviously, that's the whole reason why we do this, that models that we do train today will continue to be useful at least for some amount of time, right? If I train a model today that's going to predict me which insurance claims are going to be fraudulent or which customers are going to churn, I plan to use that model a little bit in time going forward, right? Not just for the next week, but hopefully as long as I can, right? Eventually it will break, every model does, right? And models degrade silently, but they need to be valid. They need to hold on new data. Now, I say that this is maybe the biggest difference between machine learners and statisticians. In statistics, or what machine learners will tell you, and we'll come to that, is in statistics, we use a lot of the same algorithms, right? Or a lot of the same fundamentals. The difference doesn't lie there. But in statistics, it's more like about, well, the model fit, right? We have 20, 30, 40 examples. We fit some kind of parametric assumption, and parametric there meaning, well, what we think is kind of an underfitting by design style of model that we fit to the data, and then we look at the goodness of it. Machine learners say, well, we don't care, because we have algorithms that can fit every data set that you give me perfectly. What I care about is, will it still fit well tomorrow on new data that I didn't use at all during trading, during development, during the building, during the construction of my model. And then you can even go wild. You can cheat, you can do tricks, whatever, right? But it needs to hold, it needs to work still on new unseen data. And people cheat because what people call unseen data, it's not really unseen, or they will use it in some way. But whenever you put a model into production and it spits out predictions that people will use in your organization going forward, it will be used, right? And if it fails them, people will know it very quickly. So validity, the most important criteria. It should also be useful. That sounds like, well, a given, but useful meaning actionable. And that's sometimes hard, right? I've had discussions a long time ago already by now, but, and again, it's kind of the story of a churn model at a bank here in Belgium, which was actually doing pretty well, focused specifically on younger people, people in your age bracket, in fact, or maybe a little bit older. Well, I don't know nowadays, but like on the way to, you have your relationship going, your studies are finished, on the way to buying your first property, right? A house, an apartment, something like that. And that's typically a gap or an important moment at which people break their relationship with their bank, mainly because the bank that gives them the mortgage is the bank that they then stay customers with for the next so many years, right? But also for other reasons. It's generally an important moment. So the bank was focusing, or financial institution, on that age bracket, build a whole model on top of that. Snapshot today, looking at the customer, looking forward as a target, predicting. Did pretty well. And all the test sets that we tested it out was doing not bad, right? Not spectacularly, because, I mean, you don't have a crystal ball, but pretty good. Is it actionable, though? No. Because once you have a model that does a good job, is tested, it's valid, what can you do with this? Absolutely nothing. You can go to some branch managers and ask them, well, pick up the phone and call these top 20 people on our list, and are you still happy with us? All right, well, most of them, and indeed we did do that test, and most of them said, well, no, I'm not. The model was right. Why you're not happy? Well, I just went in a few weeks ago to discuss mortgage options, and the person replying to me was not friendly, right? There's always some personal story, and the fact that the person treated them not friendly is not in our feature list, but correlation and so on, right? But it's not a really nice conversation to have. And even if the person is still happy and suddenly you get a call from your bank asking you if you're happy, you start worrying, well, is there a reason I shouldn't be happy? So as an institution, as a company, you don't have a lot of actionable choices that you can make here, right? And again, it's the problem of purpose. You started to predict something without a clear plan of, yeah, but then what if this actually runs in production? What will we do with this? No idea, right? Yeah, good predictions, zero net benefit. To some extent, and this is a tricky one, unexpected, because unexpected, there are also always things that are obvious. People have a lot of gut feeling, rightly so. People know their business. Tricky because sometimes your model can come up with patterns that are maybe not the causal patterns underlying the actual effect, right? We don't deal with causality here, we deal with correlations. It's just the features that you give that drive the outcome, right? But will still nevertheless be a correlation, and where people make stories about it and they will not trust your model or not believe it or dispel it and so on, right? So unexpected to be interesting enough, but not so weird that it drives people away. And I will give some examples of that in the next slides. And then maybe, well, a bit less, or maybe a bit again. It's a bit of a difficult topic, but understandable. If you use so-called white box techniques, and white box meaning models that are by themselves easy to interpret. So your standard decision tree, linear regression. You can make a linear or logistic regression in Excel, you look at the coefficients, you know what's going on. A decision tree, you can print it out on a slide, you can go through it, you understand what's happening there. Versus black box, which is the realm of, well, what if you put 100 decision trees in an ensemble, or again, you have a neural network with 4 million parameters, no one knows what's going on, right? How did my model come to this prediction? And that's also important because you will get a tsunami of questions asking you, well, why did this person get 0.4 in terms of probability? Why not higher? I don't believe your model. Or what are the most important things that now, out of these 200 features that we have, drove your model to construct its whatever internal model or its internal idea? So that's how you gain trust also when you try to sell your model and so on. And it's, again, a bit of a tricky one because nowadays, if you work in the more generative AI scheme, you can ask ChatGPT, like, why did you say this, right? And again, it will come up with some sort of answer. That doesn't mean that you have a real insight into, well, what's the exact way why it generated the tokens that it generated right now, right? And with so many parameters, that's pretty hard. So we'll also look at some interpretability techniques. To some extent, at some point they will all fail. Once your models become so parameterized that there is no way to get insight into them, they fail, right? And we can try to do some things there. But that's also something important, especially also when you are in an organization which is on their first steps in implementing these kind of things. Trust and understandability is another key criteria here. So as a couple of examples, so I don't know, this is an old story, has been retold many times, and luckily Gwern did good research on that in terms of figuring out that it was kind of not completely true or misspoken or retold too many times. Who knows the tank story in neural networks? One? So, like I said, it's an old story. So it's about, I think it was the US Navy or something, or some military branch of the US in the 80s. That's how the story goes, at least, right? And they were experimenting, already at that time, did exist, neural networks, artificial neural networks. And what they did is they went into the field and they took a lot of pictures of tanks, like you see here on the left-hand side, in the field, and pictures without tanks, because they were hoping that this technology could help them to detect enemy tanks, right, in a real combat scenario. And they went back with all of their pictures. They trained for a long time their neural network on the way reduced pictures, because, again, computers not very strong at that time. So they had some low-resolution pictures that they took, trained their neural network, worked perfectly, separated out a test set, and it could indeed detect from the pictures whether there was a tank in the picture or not. They went with this system, this model that they had made, to their higher-ups, and they said, well done, but we don't really trust in this computery stuff, so you really need to do a field test, right, a proof of concept. So you go out there, and you take some new pictures, and you really test it in front of our eyes. And they did it again. They went out there the next day, took some new pictures, pictures with tanks, pictures without tanks. The model failed completely. Completely broke down. And so the scientists, they were scratching their heads. They looked at the model again, did some tests again, didn't know what was happening, right? The way how the story goes, and like I said, it's not completely true, has been figured out, but they did experiment with this. But the way how the story goes, what went wrong in the end, what they finally figured out is, if you see the left-hand side and the right-hand side of this picture, apart from the fact that the left-hand side contains a tank and the right-hand side does not, what else strikes you? Grass. Bottom half of the picture? And the clouds. Exactly. What the network had learned is to detect the weather. All the pictures they took in their first test were on a clear day. And all the pictures they took in the next test, with tanks, without tanks, were on a cloudy day. So their test set, their train set, both of them were messed up. So the model was not generalizable, right? And it's easy to have these things sneak in. Now, that's a story that didn't really happen. Things that did happen, though, is self-driving cars. I already mentioned it. Udacity, at one point, tried training a self-driving car with reinforcement learning. Okay, you need to come up with a reward function. What's a good self-driving car? If you can keep some sort of constant speed, because if you do not keep a constant speed, that means that either you're flying off the bridge or you came to a stop and you crashed. What did the car learn? Well, if I just drive in circles all the time, I'm optimizing my reward function. NASA, this I really like for some reason, they also ran a similar algorithm. Let's say that we have a crew of 3 people. We send them to a Mars scenario and something goes wrong. And we can't save them, right? And they need to survive with the things that they have available there. There is some food, some water left, some basic oxygen and so on. What's the best way? Optimize me a plan that the team can survive for as long as possible. Kill off 2 of your crew members, right? Maybe even eat them, I don't know. But then the team as a whole survives as long as possible. So if you optimize for something, reward functions are not always well defined. Nevertheless, the fact that if you build a model for something, it will not generalize well to your actual use case. But that's what we are about in machine learning. We are about generalizable correlations. Causation, we know that we can't do that, right? It's not our field. That's a weakness. We admit that. We want to find generalizable correlations, maybe not forever, but for as long as we can. So that's validity. Second one is useful, actionable. I already gave you the example of, well, we can predict who will churn and then what. There are other examples. Netflix price is also an old one. At one point, Netflix is an old company by now, they wrote out a $1 million, now that's maybe too little, but at that time, $1 million price if you can come up as a team with a system that improves their recommendation engine. So if you open up the homepage of Netflix, you get some movies, well, make that better. And here is a data set that we release, anonymized, of users in the rows and movies in the columns with their ratings. That's what you have. Just based on this, make it better. Two interesting things. There indeed was a team that managed to beat Netflix at their game. They made it 1, 2, 3% better at recommending. They got a prize. Netflix never ended up implementing that system. Why? Because the whole model was so convoluted, so heavy, was a stack of models, that when even the engineers at Netflix looked at it, they said, well, we can keep this running for maybe a month or two, but then if something breaks here, this is just a mess of spaghetti code or libraries that we need to pull in. It's not worth it. Right? So they got a prize, but they never implemented it. So useful, actionable, no. And the second reason why it was not useful or actionable for Netflix is because they also got sued during that time. Because even though they had anonymized the data set, while a lot of scientists were busy working on improving their recommender algorithm, of course, you always have scientists that cannot help themselves. So you had some people that said, well, yeah, it's anonymized, but what if we try to match the ratings that we have here of a user that we do not know with things that we can find reviews on IMDb, public websites, public movie review websites. And they managed to find a couple of people that matched exactly with the data set that Netflix had released. So yeah, they got sued and they had to remove those people, right? So that's how you can also make money. Sometimes it is actionable. Sometimes you get weird questions, like I've had cases. I also teach for a postgraduate course, and I've had people working in the healthcare industry who came to me with a very weird dissertation topic, and they said, well, I want to make a model that predicts me. We have a system here that scans blood samples, and it gives some kind of green, orange, red score on the blood sample for some kind of rare disease. I forgot what it is. And I want to predict that. And first question, if you think back about the purpose, is, yeah, but if you have such a model, what do you want to do with that, right? You already have the machine. You load in the blood sample, right? It spits out a whole list of technical details and then a warning light. But you have the machine. Why do you need a model? You just use the machine. And they said, well, we know, but our purpose is the whole thing, or the whole way how this thing goes from these technical numbers that are there to that warning light is proprietary. It's part of the company's intellectual property, and they don't want to share that with us. So actually what we want to do is we just want to train a model so that we can reverse engineer this system that they have internally that we have already been using for months, so that we can get a bit deeper insight in what that thing is actually using, or what the numbers, how are they combined. Okay, fine, then that's an explanatory purpose, right? You want to get an insight, right? So even in this case, you have all the numbers there, you have your features, you have some sort of output, you want to explain it a bit better. So that next time when we talk to the company, we can say, actually, we kind of know what you guys are doing, right? Or we get some knowledge, or we extracted some knowledge that before was part of your intellectual property. Then it's actionable, then it is useful. Another case is a bit messy, but sometimes supervised learning does not give you novel cases. And this was a case also with an insurance company that I can mention that I worked on. It's actually pretty fun. It's about workers' compensation. And the way how it goes is, you know, if you're employed and you well, you would fall or you would meet an accident at your place of employment, right? Not that you guys will ever work in a factory, but if you would like fall down or your hand gets crushed in a machine or something like that, the company is of course obligated to pay you out until you're healed or forever, basically, if you're never healed, right? Because it happened at your workplace. Of course, the company is insured for that, right? So the money is not actually paid by the company itself, it's paid by the insurer. And it covers things such as even when you're on your way to work or on the way back from work in your car. Sometimes if you get an accident in your car, you're also covered. You might think that fraud, in that case, that doesn't happen. Of course it happens, right, in a lot of ways. How does it happen? In the morning, you fall off your stairs at home, right? You pull yourself to your car, you drive to work, and then you go, ah, I fell. That's how it happens. Or another typical pattern is exaggeration of damages. Exaggeration of damages. So you have people saying, well, I hurt my back at work, and sorry, doctor, 6 months later, my back still hurts. Back pain is one of the best things you can do if you ever want to be sick. It's hard to prove, right? Now, these people have private detectives, and they check your Facebook page, and they have people that they follow for a long time, and they can tell you, this guy was in Egypt last week, enjoying a margarita in the sun. Meanwhile, he's still getting workers' compensation from his company or their insurer. So try to build a model for that. The first attempt that we did, and again, that's kind of a beginner's mistake, is, okay, we can use supervised modeling on this. Do you have historical examples? Now, these private detectives, they have about 3 or 4 of them. They can maybe do 4 cases per semester, something like that. So per year, max 15. So you do not have a lot of historical examples, especially not positives, right? You have a huge class imbalance there. You know that in the negatives, probably there are some cases that currently you're labeling negative. They're not fraudulent, but just because you didn't spot them yet. So you also have noisy labels, right? If you try to build a supervised model on top of that, what do you think will happen? You would expect, well, it's probably not going to work that well. It actually did work not bad. The accuracy was not that bad. But the cases that it found, when we went back to the stakeholders and the private detectives, even although we were quite surprised with the performance of the model, what they told us is, yeah, but all the top cases that your model is finding are exactly the same cases we would have found already or would have checked already if we would have had more time, given our current rule-based system. We have some internal flags and things that we check. We know these cases. We just don't have the manpower, and they're maybe lower worth, but they're not that surprising to us. So we just rebuilt, because the way how these historical labels were set, you just have a copy of the rule-based system that was already in place. That's where the labels come from. We would have expected that your approach can give us something novel, something new, some new cases. Well, it can't, right? If those are your only positives, it can't. What we did then, and that's why unsupervised learning or anomaly detection is still so important, switched gears, throw away the labels, full-on anomaly detection, and then things started to happen. Right? You can't prove that the anomalies that you find are really fraudulent, but at least then they started saying, but actually these look interesting to us. That's weird. Right? And then you make a feedback loop where you have a person look at the anomalous cases from time to time, you label them, and you feed those in to your supervised model. So again, if you think about actionable and useful, it's more than just the algorithm and applying it, right? Unexpected, well, here are a couple of examples. UPS drivers where the route optimization model said, well, you don't take the shortest route, take more right turns, because that's faster, right? yeah, credit companies or banks, if you file out an application form online, if you type with proper capitalization, you're more credit worthy, right? There was one company a long time ago, I think it was Admiral Insurance, who made a deal with Facebook to buy customer data from Facebook to also use that in their core insurance policy. And same system, they said, well, if you are very punctual, if your comments are very precise and you use the right spelling and you are very correct in your time indications, then you must be a more punctual driver as well, right? That's a bit unexpected, maybe not fully, but interesting, right? When you fill in a CV online or you apply on LinkedIn, the browser that you utilize, it's already a feature that's being used to score you. Do you use Edge or Chrome, Safari, Firefox? Even if you buy at luxury stores, like Louis Vuitton or something, the flow that you get or the errors that you get, try it out on Chrome versus Safari, you will also see different outcomes there, right? But not everything, of course, is interesting or valid. So again, correlations versus causations, we just hook or try to get as many features as we can, and we try to hook into them. But not everything is, of course, valid in the sense that that's the true reason behind it. Interpretable, like I already mentioned, yeah, lots of questions such as, why does your model predict this outcome versus that outcome for this case? So case dependent, I don't agree. Can you explain me which features are important? Which general features did your model use? Explain me age, always a favorite. It's always the most important feature in any model that you build. How does age drive the outcome? Well, it's maybe not linear, right? It's maybe not monotonic, but can you show me something like how is the outcome, how is that impacted by age? And yeah, especially in early movers, like these things can look a bit scary, obviously. They are like people with a lot of gut feeling and background, and now there is a team of data scientists and they tell you just trust us, right? I've had one company tell me, well, we don't use the term black box model anymore. We now call it, it's an unexplainable model. Yeah, but it's an easy way to lose trust, right? So understandability, getting an insight, building a culture in how these things work is also a key criteria if you want adoption of these things. And then finally, yeah, maybe also ethical, fair, humane even. We do know that we live in a world where we've had lots of examples. Here are a couple of older ones. Every time models are being utilized, we embed the biases that we have in our environment into them. Even although they're so-called objective or mathematical, right? Objective is, people say, well, this story, for instance, was about recidivity. When you are a judge and you need to decide, can I release this person back into the world? What judges, especially in the US, do is they try to take into account how likely is it that this person will commit another crime. Now, there is a case to make. Judges are humans, right? And everybody thinks a little bit amongst themselves, so this was not objective at all. So at one point, there was an attempt to make this a bit more systemized. Let's make a model. Let's take the whole history that we have of cases and the decisions that judges made, and let's put that into a predictive model. Well, until someone goes to look at that, and the problem lies, of course, in the fact that if you take the exact same person and your data set is big enough that you can do that for the exact same type of crime, very similar background, very similar upbringing, with only one difference, the color of their skin, that the model predicts something else. Yeah, you can say it's objective, it's mathematical, but sure it is, the algorithm is, but your whole training data set is not right. And even just as a person, you would not agree, like, okay, everything else being equal, if that's the only thing that I differ on, then the answer of your model should have been the same, right? So same for well, text embedding models that have hidden sexist aspects in there. And even up until today, of course, like I said, we live in the age of AI. There are a lot of studies that are being done on, well, cognitive debt when using ChatGPT, right? And we have all felt this. If you talk too long with ChatGPT, you go into some kind of slumber, right? You're totally right. This is brilliant. 3 a.m. Yes, absolutely. You should, whatever you're thinking about. But it's, so there are also, of course, ethical aspects here, which is a bit more out there, but still important today. In terms of process, so again, a bit of an describing the analytics process and today AI process. You will see that if you try to define it a little bit, always the same aspects come back. Two things about that. They will always start, whatever process you try to look at, like this very old one, with, okay, first you need to gather the data or define your business question, then you hunt for the data, you clean the data, you play with it a bit, you build your model, and then there is this final step where you interpret a little bit wrong here because all of these things are lumped together. Interpret, evaluate, and deploy the model all in one, right? It should be split up, but they all more or less follow the same pattern, right? This is from a paper from '96, or where this was first proposed, the data knowledge discovery model from databases with, and that they got right, a huge part in pre-processing. That's true, right? So whatever you spend time on or whichever data set that you will work on, pre-processing does take up 80% of your time. Especially if it's the first time that you use a data set, you can multiply it by 3, your estimate. So that they got right. Bit more modern is something called CRISP-DM, the cross-industry standard process for data mining. Also maybe reveals that it's already a little bit old. They were planning to make a second version of this, which never really happened, but it tells more or less the same story anyway, right? So it starts with you need to understand the business question, good. Then you go hunt for your data, you prepare it, you do some modeling, you evaluate it, and you deploy it. And what they got right is they put a big, huge circle around it to also indicate, well, even after you're done with your deployment, there will be some time when you need to revisit that model and maintain it, or maybe take it out of the box because models degrade, right? So that other continuous thing, right, that they got right. If you ever want to become a data quality or quality guru in general, take whatever thing that you draw and put a big circle around it and say it's continuous and you're golden, right? So yeah, I mean, it's saying something. There are others as well that have been proposed. There is SEMA, for instance. SAS came up with that at some point. Sample, explore, modify, model, and assess. Okay, same thing. Jeremy Howard and his team came up with the drivetrain approach, which was a little bit different because at some point, or for one, it's pretty simple, but also it starts with a clear objective, and then also very clearly, well, from the beginning, we should know what are actually the inputs that we can adjust, whatever the prediction that we get from this model that we're building here, what do we have influence on versus the things that we do not have influence on. Pretty interesting idea, but they're all more or less the same. It's like, okay, question, data, building, evaluating, right? And then at some point deploying. If you look today, well, this is AI agent development, right? It starts to look less and less like a process, but it's like a mix of things. But again, I mean, objectives, preparation, tooling, and deploying, still the same things are present nowadays, even if you look in how do I deploy or employ AI in my organization. It starts to become less and less, of course, because there's no time for this kind of old, boring process charts when you're vibe coding. But still, we've been doing the same thing for a lot of time. Now, the real one looks kind of more like this. And that's what's not so bad about CRISP-DM, is that it also contains arrows back. And that happens very often. The thing being is that upfront, the business question that you get impacts the data that you will select. And the data that you find will reshape the business question. So already in these 2 steps, you will go back and forth a whole lot. And then later, you try to pre-process your data a bit, and you try out some models, and then you go back, and people are not very happy. And then at some point, someone will say, ah, yeah, but actually we have been thinking about this all wrong. We have been asking the wrong question. So it's still very hard up until today to measure or estimate the timeline or the time that will be required for ML projects, let alone AI projects. It's very hard to do. Because for many organizations, this is still a discovery pattern or discovery route that they also have through their own data. But that's normal, right? So that's okay. You do need to go back from time to time, and you need to re-ask the question. And like I said, start with the purpose and start questioning, okay, but let's say we're already at the end and we do have our model. How do you actually plan to utilize this? How does this fit in your day-to-day needs? Or is this just some idea to score that you have? So managing these kind of insights, there have been a lot of ideas that have popped up over the past years. Well, waterfall, of course, doesn't work, but also trying to take machine learning or data science as some sort of agile methodology also doesn't work. Agile typically goes too quick, whereas in data science, you need more time to experiment, especially at the beginning. Same for Scrum, stand-ups, Lean, model factories, and then even later solutions such as AutoML, automated machine learning. Up until today, like everybody's vibe coding or we use a swarm of agents, we do not have yet a clear managerial guide how you can manage the discovery of these kind of knowledge products, how you can manage insights. It's very tricky to do. I think the solution is it starts with bringing the right people together, but then other than that, decentralized, centralized, business up or top down, it's hard to organize. And none of the tools that we have so far, and you see that even today, there are loads of companies that are jumping on the AI bandwagon and they want to do something, and then it either, well, often it doesn't work. And why? It's weird. And then you have other companies, typically very engineering-driven companies, but again, it's maybe more part of the culture, where it's more embedded, this sort of thing. Very hard to solve. There have been attempts to try to discuss this. Well, it's not wrong. What's the issue? Misalignment of technical and business expectations. Data science projects, AI projects, machine learning projects are ultimately consumed by business teams. However, those projects often start without a clear alignment between business and data science teams. How could they? Data scientists are good at the data science. They know their data, they know their algorithms, and so on. Business people are good at their business. They oftentimes do not have a clear way to communicate. Or oftentimes, when they are pushed into a way to communicate, there is no clear time frame behind it. Or it's fast, 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 an overwhelming amount of models and ideas that ultimately you end with the model factory, where you have 20 models that all kind of predict more or less the same thing. Because business people, when you give them a panacea of, well, we have this promising idea of AI and so on, what will they ask? Increase my revenue. Predict me which customers will be best and so on. So you get a collection of models that do the same thing. So it's a bit of a difficulty that you do need to accept in some way, that if you want to jump into this, especially as a large organization which is not embedded in this, that this is a changing technique, that is, the role is to change profoundly your way of working, and you need to give it some space to grow into that. And that's a mistake that is still being made today, even with AI. Same here, another paper. Practitioners face challenges at each stage of the machine learning deployment workflow. That's also why I said that in this process chart before, that deployment at the end sounds easy. Deployment is oftentimes the hardest step. You're done, your model is trained, it works well, and now the whole embedding in the IT system of the organization. Who will maintain it? Who will document it? Who will use it? In the past years, this has been renamed or adopted as ML Ops, Operations of Machine Learning. Still a huge challenge. You also find books about AI Ops today. And there typically they talk about using guardrails and using LLMs in the right way. Same questions, different technology. Still unsolved. Same for roles. If you would say, well, what do you want to become later on? An AI expert, a data engineer, a data scientist. The roles have been shifting as well. I think most companies nowadays, they make a difference between junior and senior roles, but also not always in the right way. Juniors are typically the people that need to extract data from the database using SQL, and then the seniors, they are the ones who can play with the algorithms. If I would be a junior, after a couple of weeks, I would burn out, to be honest. So that's why there is a lot of both big data projects, ML projects that are still failing. We experimented with it, we tried it, it didn't work for us. Same for AI projects. This is my old slide, and this is news articles from a week ago, exactly the same thing. MIT did a study, 95% of enterprise AI fails, right? So the challenges are still there in terms of managing this, in terms of getting value out of this. Definitely not easy. So yeah, with that being said, it's not all bad news, because after this introduction, from next week onwards, we will get started with our supervised learning essentials. Good? Good. Next week is theory. See you then.